deploy a capable language model to assist a legal team. It drafts a brief, cites 5 federal cases, and summarizes the precedents perfectly. Then the opposing counsel checks the citations. None of those cases exist. This exact scenario has repeatedly played out in the federal court system. By 2026, legal analytics trackers counted hundreds of court cases involving AI-fabricated citations, leading judges to formally sanction the attorneys responsible. This map tracks the financial fallout. In the Central District of California, 2 law firms were ordered to pay $31,100 in fees after submitting a brief filled with hallucinated citations. The Sixth Circuit handed down a similar $30,000 sanction for fake cases. These failures share a specific signature. The model is confidently wrong because it is generating text from its internal weights rather than a verified external source. Early on, developers assumed that scaling up the models, adding more parameters and training data, would eventually eliminate these fabrications entirely. But a larger model cannot memorize every detail of a private company's internal wiki or a newly published legal statute. If the exact factual grounding isn't provided at the moment of generation, the model will interpolate and guess. This operational reality forced the industry to pivot. Production systems now require a strictly enforced grounded or refuse mechanism, pairing generation with mandatory citation verification. If the system cannot link a claim to a retrieved document, it must abstain from answering. Fixing hallucination isn't achieved by waiting for a smarter text generator. It is achieved by strictly engineering the text that you place into the model's context window. To build that context window, we need to construct a highly tuned retrieval pipeline. This diagram maps out the 4 mandatory stages of a modern retrieval engine. If any stage is misconfigured, false citations slip through. We start on the extreme left, where raw files, PDFs, code, and manuals enter the system. These documents are forced through a strict sequence of mathematical filters. They are broken apart, converted into vectors, searched, and reordered until only clean, highly relevant context remains. The goal is to assemble these blocks into a sequence where every stage adds a specific layer of verification to the data stream. The first critical operation is chunking. A massive document cannot fit into a database or a context window all at once, so we have to break it down into digestible pieces. This image details the outdated baseline, naive, fixed-size chunking. It cuts text by a strict character limit. Counting characters rather than meaning, the window blindly slices mid-sentence. This severing strips chunks of context, leaving fragments like the company unanchored without preceding nouns. To prevent data loss, modern pipelines deploy structure-aware chunking and contextual retrieval. During ingestion, an LLM processes the full document, generating a short, orienting description for every chunk. By prepending this description, an isolated paragraph permanently maintains its antecedent meaning before entering the index. This chart visualizes the benchmark data for contextual retrieval. When combined with a re-ranking stage, prepending these context tags drives a 67% reduction in retrieval failures. Running an LLM over an entire document for every single chunk used to be cost-prohibitive. The widespread adoption of prompt caching makes this prepending step economically viable at an enterprise scale. Slicing text for semantic meaning, rather than relying on raw byte counts, is the structural prerequisite for preventing out-of-context hallucinations. Once we have contextualized the text chunks, we move to the embedding stage, where the words are translated into mathematical coordinates. Dense semantic embedding converts the underlying meaning of a text segment into a long array of numbers, plotting concepts with similar meanings closely together in a vector space. The historical bottleneck with this approach is memory. Storing massive, high-dimensional vectors for millions of chunks requires a tremendous amount of database RAM. The modern solution to this memory bottleneck is Matryoshka representation learning. Models are explicitly trained so the very front of the vector, the prefix, contains the most critical information. This lets you cut off the end of a 3072-dimension array, yielding a 12-time storage reduction. The system maintains high retrieval accuracy even on that highly compressed prefix. Matryoshka learning transforms high-fidelity embedding into a granular trade-off between storage costs and retrieval precision. With the database populated, we move to query execution. The user asks a question, and the system must fetch the most relevant chunks. This diagram illustrates the hybrid search architecture, revealing a flaw in relying solely on dense search. Semantic vectors excel at finding paraphrased intent, seamlessly connecting a query about getting your money back to a document titled refund policy. But dense vectors ignore literal unique tokens. They struggle to retrieve specific SKUs or hex error codes. To catch those exact strings, pipelines run a parallel lane of sparse BM25 retrieval, relying entirely on exact keyword matching. Combining these two systems creates a mathematical problem. Dense cosine scores and sparse keyword scores operate on totally different numeric scales, making direct comparisons impossible. Reciprocal rank fusion bypasses this scaling problem entirely. Instead of comparing raw scores, RRF evaluates chunks based purely on their rank position in each respective list. Fusing meaning-based vectors with literal keyword matches yields a strictly superior candidate list than either individual technology could produce alone. The fused list generated by the hybrid search typically surfaces about 50 candidate documents, but that pile is still too noisy to safely feed into a language model. This visualization shows the final architectural gate, the cross-encoder reranker. The earlier retrieval pass was fast and approximate, comparing the query against millions of documents by evaluating their vector representations separately. The cross-encoder is computationally expensive, but highly precise. It processes the text of the user's query and the specific document together in a single forward pass, capturing exact match nuances before outputting the top 5. This retrieve-wide, re-rank-narrow architecture acts as the final non-negotiable filter. It guarantees the model only ever sees high-signal truth. Let's step back from the workbench and evaluate the real-world performance of this finalized pipeline architecture. This chart illustrates empirical metrics from the Vectara hallucination leaderboard. Under perfectly grounded summarization settings, hallucination rates for the best models plateau in the 1.5 to 8% range. The data reveals a stubborn floor. While these retrieval upgrades cut failures by 2/3, the baseline hallucination rate never hit 0. A perfectly engineered context window is mathematically necessary, but it is not sufficient to guarantee absolute enterprise safety. What remains is a final operational requirement. The vulnerability lies in standard generative architecture. By default, a model operates without any mechanical boundary separating the retrieved truth it was handed from the text it is actively generating. To fix this, we have to build a tripartite system. We isolate the agent's memory stores, treat the RAG pipeline as a strict read-only tool, and deploy an uncompromising output evaluator to check its work. Production readiness means wrapping the model in a hard engineering harness. Let's start by physically separating our data sources. The external document corpus serves as our authoritative truth. It is strictly read-only. The agent's accumulated memory, on the other hand, is its experiential state. As of LangChain version 0.3.1, legacy chain memory classes like conversation buffer memory are completely deprecated. Modern LangGraph architecture relies entirely on explicit state persistence. That persistence splits into 2 layers. The first is working memory, handled by a checkpointer. This is strictly scoped to the active conversation thread, keeping track of immediate dialogue. This schematic maps out our memory-augmented agent. Notice the central agent node and its direct link to the working memory in the top left, which is keyed precisely by the thread ID to maintain session continuity. The second layer is the long-term store, backed by a vector database. Here, the agent searches for user-specific insights. Looking at the bottom left, you trace this bidirectional write and recall path. The agent curates its experience, pushing facts in and pulling them back. Crucially, document retrieval is isolated from this memory loop. RAG is deployed as a discrete tool, explicitly reserved for fetching authoritative ground truth. The agent independently decides when to query the corpus, retrieving evidence without ever altering the underlying data. Physically isolating experiential memory from curated truth ensures the agent's personalized notes never silently contaminate the verifiable enterprise data. Even with precise retrieval, we face a confidence trap. An agent armed with robust tools will still confidently output hallucinations if the retrieved context is sparse or logically insufficient to answer the prompt. To stop this, we insert a runtime output guardrail. We apply a natural language inference, or NLI, self-check that intercepts the draft answer before it reaches the user. This diagram illustrates the grounded or refuse gauge. It takes two direct inputs, the draft answer and the retrieved context chunks, feeding both into an independent verification logic. The evaluator breaks the draft answer into atomic claims, explicitly verifying each against the retrieved evidence. When a claim is fully backed, the gauge registers it as supported. The system approves the text and emits the answer with strict citations. If the evaluator detects a gap, it triggers a strict fallback. If any single claim lacks explicit source support, it trips the refusal threshold. The system drops the draft and abstains, escalating the issue rather than guessing. This hard refusal architecture trades a slight increase in I don't know responses for a massive drop in confident falsehoods. In regulated environments, that trade-off is a non-negotiable requirement. Remember, a hallucination is simply a missing guardrail. Enforcing strict NLI entailment at runtime structurally eliminates fabricated claims. Runtime guardrails protect live traffic, but they must be mathematically validated against golden datasets in your continuous integration pipeline before deployment. We achieve this using the RAGAS framework. It acts as an automated LLM as a judge, running independently to isolate retrieval failures from generation errors. This is the RAGAS metrics matrix. It sharply divides your pipeline's performance into retrieval quality on the left and generation quality on the right. Under retrieval, we measure context precision. This scores whether your engine surfaced the highest signal chunks at the top of the ranking. Below that is context recall, measuring what fraction of the required ground truth evidence actually made it into the retrieved chunks. On the generation side, answer relevancy scores whether the text strictly addresses the user's prompt, penalizing off-topic drift. Finally, faithfulness is the ratio of supported claims to total claims, acting as the primary metric that catches hallucinated logic. These numbers act as your deployment gates. Automated pipeline merges should strictly require both faithfulness and context recall scores to clear an 0.8 threshold. Deploying these decoupled metrics turns the subjective feeling of output accuracy into a highly auditable, quantifiable engineering standard. Now we bring it together. Experiential memory, the read-only RAG tool, and the NLI guardrail converge into a single, seamless live execution trace. Watch a live data packet move through the system. The system's reliability is manufactured entirely by the engineered constraints surrounding it. Ending hallucinations is not a prompt engineering task. It is a strict architectural choice, achieved by locking generative capabilities within verifiable mechanical boundaries.